Okay, welcome to the last talk of this session. And the speaker is Professor Luis Orozco from University of Maryland. And he will talk about Francium and fundamental symmetries. Let's welcome.
Well, thank you so much for being here at the end of the day and talking about something completely different. I feel to a certain extent honored, to a certain extent. It's an odd position. But it is very important to do it today because you see, I'm talking about Francium. And what day is today? 14th of July. Vive la France! It's the day, the National Day of France. So thank you very much to Jehan who managed to get me invited here. I have been having some fun. And look, what I'm telling you today is starting with history, then a story, and then a dream. Okay? So it's in these three sections. So the history is actually a little bit, I find it very exciting and very, the history started, oops, wrong way. The history started about 150, 160 years old. So it started with Mendeleev when he published uh, his first version of the periodic table. So, oops, what happened? The first version of the periodic table of Mendeleev in 69, right? If you look at it, he put lithium, sodium, potassium, rubidium, cesium, and he messed up. The next one in this point should have been francium, and he put thallium. He really but it's amazing that already in the first periodic table, he already had all that. So a couple of years later, not a couple of years later, by 71, he published a new version of that. And now you recognize lithium, sodium, potassium, rubidium, cesium, and now there is an empty space. Okay, so he agreed that there was there was something missing, and but no, this is not the only empty space. So you see, aluminium has an empty space down here, right? And so there are empty spaces all over the place. And then he decided that those empty spaces will be receiving a rather odd name, and the odd name would always start with the preliminary word eka. So the one below cesium would be eka cesium. So that's the name with which people will start saying, oh, we found it. And the findings started to happen in 25 when a Soviet chemist said, I found ecacesium and it's going to be called rusium, and nobody was able to find the ecacesium that he had found. Then in 26, two people in the UK analyzed spectrum, X-ray spectra of manganese sulfate, and they said, sure, absolutely, there is another element, and we'll call it alkalinium. In those days, you named immediately the well, in 31, Allison and Murphy from the Alabama Polytechnic Institute, now Auburn University, analyzed some pollucide that came from the state of Virginia. He came from the state of Virginia, and he said, this is called Virginium, and nobody could reproduce it. Then Holbay and Grachois in France analyzed again pollucide, and they say, yes, there is something, and they call it Moldavia. Well, all of those were false alarms. And now I'm going to tell you the discovery of francium. The discovery of francium happened because of an absolutely marvelous woman. A woman. Okay? I really admire her, and I hope some of you follow her life. She was born in 1909 in Paris, in the east part of Paris. That means in the industrial part of the city. It's not the fancy part of Paris. She was the youngest of five kids, and she had dreamt all the time to study medicine, but her father died, and she had to make life, uh, help to eat, and so on. So she went to a technical school where she became a chemistry lab technician. That chemical school had a deal with the Curies that all of us have heard about, Pierre and Marie. By that time, Marie was dead. Sorry, Pierre was dead. Marie only was alive. And she had a deal, Pierre had done, that they will hire every year the top student in the school as an assistant. So she was 19 and she was called for an interview. So she was 19, was called for an interview. She went to the interview, and she later related, oh my, that lady looks like a witch, and I am so scared I'm not going to get the job. This lady was dressed in black and okay, 2 Nobel Prizes on her, and it's like, and this 19-year-old, well, guess what? She was given the job. But now, we physicists, experimental physicists, like the three I know that we are here, are used to sometimes to work hard. I know Johan works hard, but if you are 19 years old and you are given 10 tons of mineral, imagine like a room like this full of mineral, and then you're told, oh, your task is to purify and find the actinium on that. So she had to grind it, do chemistry, and slowly. From 10 tons, she got a few milligrams in basically 10 years. By the time she had her sample, the 7th of January of 1939, she had a few milligrams. She discovered that the actinium that she had two decays, not one, but two decays. One at 220 keV, corresponding to actinium, and the other at 80 keV. She was only detecting the betas, right? Uh, of the daughter with a half-life of 21 minutes. And I've been able to get a hold of the of her logbook, and in the logbook she says here that she's got the actinium in a solution. So you see, actinium and lanthanum are similar. So she was following the chemistry of lanthanum. She had only gone to technical school. She hadn't a PhD. So she says, well, I'm going to use what I would use for lanthanum. Then she saw that the daughter behaved like an alkali, because if you can see that over here, she says, I have the solution, and now I add cesium chloride. She adds the cesium chloride, and the alkalis change. So if you're an alkali and you're cesium, francium takes your place. And so she could then extract the francium chloride. Sorry, I'm saying francium, but the new alkali chloride, okay? And then she saw, yes, it's an alkali, it's element 87. And it has a lifetime of 21 minutes. This is the closest I have seen in a logbook to an eureka moment. She didn't make any fuss, but remember, no degree. This is what she actually did. She had actinium 227 decayed to 223 plus an alpha particle. And then when the francium decays, it produces the beta that she was measuring. This is impressive. This is extraordinary. This is the work. This is the result of hard, systematic work that we know in science and in mathematics. You just cannot stop. Okay. This is her in the laboratory. If you are ever in Paris, you can visit the lab. It is the Radium Institute. It's the Museum of the Radium Institute. And by the way, these is still there. So you can actually see that. It's extraordinary. So, and remember which day did she find the francium? The 7th. So we all hear about, oh, I want to publish really fast. You see when it got published? Not bad. And I don't know how many of you recognize this name. Jean Perrin was a member of the Academy of Sciences, and that's why but he won the Nobel Prize for the measurements that confirmed the existence of atoms in one of the 7 proposed methods in Einstein's PhD. 7. Not bad. So Einstein was very worried that the physicists were not convinced of the existence of atoms. And he proposed 7, and Jean Perrin did it with the random walks, and he was able to do the drawings and measure the diffusion and so on. And so here it is, the number 87. It leaves 21 minutes. To today, that number is correct. That's extraordinary. Okay, so, and here's what I was telling you. There is a decay by beta. Okay, so that was the story. Remember, she was just a technician. She got a fellowship to study her PhD in La Sorbonne. Remember, they got some neighbors arrive in Paris and stay for 4 years, right? So it was hard, but she did study during the invasion of Germany and eventually got her PhD. She became a professor and the head of nuclear chemistry in 1949. And more important, she was the first woman ever elected a corresponding member of the French Academy of Sciences. Marie Curie was not, because she was a member of the medical academy, not of the Academy of Sciences. But she was elected through the medical. And some people may say, well, why was she not a full member? And you're going to laugh at my explanation, but I asked a member why. Up till 1980, to be a real member of the Academy, you had to be within 1 day by horse ride of Paris. And she lived in Strasbourg, which is about 200 kilometers away. You cannot get by horse. You can get by train, but not by horse. But the rules of the academy said, okay, so she was the first she was the first corresponding member of the French Academy in 62. And for those of you who want to learn about her wonderful life, read this article in the New York Times Magazine. The title is fantastic, right? My great-great-aunt discovered francium and it killed her. Okay, so I really strongly recommend it. So and then on a very, very positive side, the new university in France, in Paris, which is called Le Paris-Saclay in Palaiseau, in the south of Paris, now has the metro station is named after her, and there is a square named after her. So I am so glad that there is recognition for this. This is not the very politically engaged and this and that. No, she just worked very hard. Okay, so now I want to go to the story. This is the part that I want to say about the entrance of atomic physics. So all I told you before was nuclear physics. You may finally ask, well, why did she call it francium? She was given a first question. She was asked, and she said, well, why don't we call it actinium K? And by that time, the International Committee said, no, because we already have actinium and protactinium. So no more actiniums in the periodic table. Then when she finished her PhD, she was asked again, okay, how are we going to call it? And she said, cation. And then her boss, which by that time Marie Curie was dead, Irene Curie, said, no way, no discovery in the Institute of Radium can be called the cat. What element is it? The cat? No. And then eventually she, a couple of years later in 47, said, well, why don't you call it francium? Okay, so and today we celebrate it, okay? All right, so the entrance in atomic physics didn't happen until 78, when a team led by Sylvain Liberman discovered what is the brightest line of francium. So for those who are not used to thinking in atomic physics, this is the equivalent of the bright yellow line of sodium that is used to be used in light in the streets and so on. Okay, so this one is a little bit on the red side. Okay, and in order to find it, he said that it was actually, he didn't say euro, he said a franc. It was like to find a coin of the size of a franc. The young people in China don't know what a coin is, do you? Something like this, look. And this is Chinese, right? So find these, okay, between I guess Paris and Marseille, that would be like from here to Hefei. Not bad, right? You have to be looking like, you have to be searching with lasers and things like that until you find it, and he found it. Okay? All right. So this is a energy level. These are not, so the ground state is an S state. This is the line that he found. There is another line to another different, so the P1 half, the P2 halves, and the one I'm going to tell you some more is this 8S state, and that's like that. Okay, so now let's continue, and I remind you that our friend, the weak interaction, well, started with a beautiful beta decay theory of Fermi. After that, we identified now that it's the guy that converts a neutron to a proton, right? Changes the flavor. Then Weinberg and Salam gave us the electroweak unification, and the proton becomes a neutron, is the way all of you explained to your grandmother how the sun works, right? Because your grandmother knows that the sun burns hydrogen and it becomes helium, and helium has two neutrons. And your grandmother says, well, where did your neutrons come from? Right? And so that's how you explain it to her, right? Anyway, so the weak interaction violates parity, the weak interaction violates charge parity, and of course neutrinos have Mars, and I'm sure they will be giving us even more surprises. All right, so basically parity says that in a system when you have spin and you have a dipole and then you apply parity, this is what happens, right? The dipole doesn't change, that changes. And time, uh, again, if the dipole is aligned with the spin, if you apply the time reversal, it's not the same. Okay, so those are the two basic symmetries that are discrete basic symmetries that are violated. So then after a couple of years at CERN, I end up in Stony Brook. I was measuring the mass of the antiproton. It's the same as the mass of the proton. Don't worry, it's okay. Yes, you All right. So I arrived there, and in collaboration with Gene Sprouse, we thought that it would be fun to measure parity non-conservation and compare to the predictions of the standard model. After all, the effects scale as C cube or a little bit better, or at C to the 8/3. So C cube is a good guess, and see if the weak interaction is affected by the presence of lots of nucleons. So the dream, of course, is to see what the coupling constants between the electron and the up and the down quark are. And there had been a very beautiful measurement. It's from early 97, yes, of in cesium that gives this band for those. Q weak but was measured in Jefferson Lab. And the hope is that one can put another line with or two with different isotopes of francium. So, but the first question, when you are an assistant professor and you don't have these wonderful visions that the people like Steve Chu always had, right? As we heard today, you see, well, how do you make francium at Stony Brook? They had an accelerator, and this is the chart of nuclei. This is the line of neutrons. This is the line of protons. And you can see here is helium and different things. And so we could do a reaction between, let's see, a oxygen. Oops. Look, we had oxygen. We put it with enough energy that there is no Coulomb repulsion. It's about 100 MeV. That fuses with this nucleus. So 18 plus 187, you end up with 215 of those nucleons. But oxygen has 6 protons, and the that with the 8 protons. Gold has 79 protons. And so when you add those two, you end up with the important number of 87, sorry, 87. And to stabilize the nucleus, you boil 5 neutrons. So I spent like the first 5 years of my career at Stony Brook learning to make francium. And at the end, we could make francium, and we could actually use some of the ideas of Steve Chu and Bill Phillips and all those guys to laser cool. And our first trap was about 2,000 atoms, and about by the end of in 10 years, we were able to. So here is the first trap out, and then we were able to have about a quarter of a million atoms. We did basic atomic spectroscopy of all sorts of things. And as I said to you, the one thing that I would like to stress is that the theory prediction for where the line was localized was known to 20% in 1978. By the time that we were looking at a particular new other line, this is what these are the numbers that we measured. And now you can see the predictions from Mariana Safranova. They were already accurate to 5 digits. So the calculational power has increased enormously. So uh, I left the university at Stony Brook and moved to Maryland, and the experiment also moved to Triumph. And when it moved to Triumph, we started a new collaboration. I am a retired professor, and Gerald Winner is the spokesperson for the collaboration. He's a professor at the University of Manitoba, and we have people from other institutions in the US, in Mexico, in Canada, and I think if you pay taxes in the US, in Mexico, or in Canada, I thank you for your contribution. Okay? So uh, the uh, the trap, which was designed, constructed, and tested by my very dear colleague. You see, I didn't say a student, my dear colleague Yang Shang. He did the design. It's a very, it's engineering, it's superb, it's physics, very subtle but very good. So I do want you to see somehow, I do know the somehow, but I'm not going to bother you. Francium is produced as an ion by Triumph. It's an accelerator in Vancouver, Canada. They deliver it to us at 15 keVs, and we deposited it in a foil of yttrium. That foil of yttrium is like that for 20 seconds. And then for 1 second, the foil of yttrium is turned up. You run in about 600 milliseconds a current that raises this temperature to about 700 C, which means the francium is going to be expelled. But why did we use yttrium? There are very few metals that will not, when it is expelled, is not ionized. The other one is zirconium. Okay, so what comes out here is francium atoms, neutral, and they can be trapped with the techniques that were developed by Bill Phillips, by Steve Chu. Okay, that he said we developed the magneto-optical trap. Yes, they did. And so that allows us to cool them. So we start at about 15 kilovolts here, right? That's the energy here. By the time they are here, maybe the temperature, now I'm going to change the temperature, and the temperature is more like, let, let's be very pessimistic, 1 millikelvin. And then after that second, we come back down and we can do physics with that. There was a very, and Jehan can tell you everything about, there is a coating on the surface of this glass so that the alkalis don't embed on it, that they bounce back. Okay, otherwise alkalis tend to stick on the glass. And so it's a silene what eventually was used. And then you'll see some results in the science chamber. But before I go to the results of the science chamber, I do want to show you something which is part of the PhD work of Jehan, of which I am very happy to show you in this place. And what Jehan did is, you see, the first thing we think as atomic physicists is that the nucleus is a point. So the magnetic moment of the nucleus should just be a point. But the truth is that it's not a point. And the truth is that the neutrons, okay, if a neutron is in a particular place and it is unpaired, it may contribute to the magnetic moment, to the magnetization. So the question is, how does that change the hyperfine splitting? And that's called the hyperfine anomaly. And the hyperfine anomaly, the hyperfine anomaly is then you have the energy, the energy levels we're going to use, oops, are the 7s 1 half, the 7p 1 half. And you see, this is the radial the radial distribution of that wave function. And you see, it has a slightly different value depending on the radius. It has a slightly different value. So depending on where exactly you put the protons or you put the neutrons, then when you take into account where are the neutrons, you may end up with a different value for the S level or for the P. So you measure very careful. This was measured at CERN. We measured this, and this is the final result. So the dashed line that you see here, so you see a very odd staggering, right? It goes up and down. Why is that? Well, if the number of neutrons is paired, so like in the case of 211, in the case of 213, right? You get this situation, the neutron doesn't contribute, but if it is unpaired, you get this situation. And this is the most interesting one because these are, in this particular case, 206, this is an isomer state. 207, dots pair, 209 is pair, 211, 12, but this tells you that uh, our current understanding, which says that the charge radius is equal to the magnetic radius, is over here. This is the nuclear structure theory. These guys are different. And why am I excited about this? I am excited about this because the parity non-conservation, the electron is going to enter in the nucleus and we better understand what the neutrons are doing. If we don't understand what the neutrons are doing structurally, it may be a difficulty. Okay? So this nailed that down. That was very good. The, the, the measurements are pretty good. Okay? And then again, Jehan was able to implement and build and do the first test. The trap connected to the accelerator is up there, and then we move the atoms to another trap, which is about a meter down, where the environment is much more controlled. Magnetic fields, electric fields, and all those things. This is in an accelerator environment, by the way, so that puts quite a bit of question. And that's where we're going to be able to do some, we have starting to do the test for parity non-conservation in the next run in the summer. But let me just say what it implies. So you have to define a system of coordinates that defines the handedness. And that is defined by the electric field that is going into the screen, the magnetic field, and the polarization of the light, sigma plus or sigma minus. So that sets whether you're right-handed or left-handed. Look, if you want to check if a system, meaning if your hand is right-handed or left-handed, one way to do it is use a globe, right? The globe is the apparatus to measure the handedness. So that's what we're defining, the globe. In terms of so we will have a pseudoscalar, which is the spin with the momentum. All right. So eventually we want to go for atomic parity non-conservation between the 6s and the 8s. What is that? So we want to excite from the ground state to the excited state, but these two states are S states. That's forbidden in electricity and magnetism for dipole transitions. That dipole transition has to change parity. but it is allowed because there is a little bit of parity non-conservation. The weak interaction violates parity. In other words, when the electron is inside the nucleus, it exchanges a Z particle with one of those nucleons, most likely a neutron. There are more neutrons than protons. So, but unfortunately, and this is the very nice result that we recently had, the this transition also has a little bit of amplitude because of hyperfine mixing. So this state, you would say, oh, you cannot have an M1 transition between two different 7 and 8s states. Yes, you can, because by perturbation theory, this guy gets mixed with a little bit of that, and now you can, right? So this acquires a little bit of the 8s, that is. And so the idea is very, very simple. It's an idea that is used in a lot of weak interaction experiments, and that is don't do the experiment, but interfere it with something which is allowed. So that's why we need the electric field. The electric field produces a Stark effect that mixes the states, but that doesn't violate parity. So when you change the globes, then you change the handedness of the system. You choose either the plus or the minus. And so at the end, the signal is what you measure when you have the plus, minus what you measure when you have the minus. And that is eventually proportional to the amplitude of the parity non-conservation divided by the Stark gap. Okay, so that's the plan, and it's going. But I do want to show you the results of of the M1 transition, because we have that. So what we're going to do is we're going to try to measure the transition, as I said to you, between this one and that one, this transition, this M1 transition. This is about 6 orders of magnitude smaller than that. So it's important to, if this dominates, we're in trouble, right? And the key part is that we're going to mix a little bit of P, all right? Through, that's what is going to happen. And we're going to drive this, and then we're going to look at the light that decays through here. So this is 506, and this is 800, sorry. This one here is 817, and this one here is 718. So this is the result. Indeed, we can see the resonance. We can see a beautiful resonance there. The signal to noise ratio is about 10, but it's there. To give you an idea of what the size is, here it is, the size. If we don't put any mixing, you see this doesn't go to 0. So this is what I just showed you, the height of this point. But then we put mixing, we can see a much, much larger signal, and we can extrapolate to 0, and we have done that. But we now have a much better way to do the measurement, and you see from the former results that I show you, now the signal to noise has improved, at least by a factor of 100. So this gives us much, much better reliability on the numbers, but we are still dominated by statistics. We do know there are some systematic errors, and we do have about a factor of 10 to the 3 more signal. So what we have now is a number. We have looked at the number, and our number is 130 plus or minus 10 in the appropriate units that Mariana Safranova uses, 10 to the minus 5, and she has a prediction of 137.4 times 10 to the minus 5. I should, extremely important for me to stress to you that this calculation is a true ab initio calculation. She didn't know the result when she did the prediction, okay? Because many times, of course, we humans just make convergence, and we also try to be very careful, all right? So that's the status now. But during the pandemic, Dave DeMille, who then was at the University of Chicago and now has moved to, or is in the process of moving to John Hopkins, right? Called me and said, "Hey, Luis, I have an idea." Yes, Dave. Well, you see, maybe we can do an experiment with Francium to look for an EDM, a permanent electric dipole moment, which, as you know, violates time reversal. Yes. What do you want to do? Well, look, if we use the 223 francium, which has an octuple deformation, so it looks like a pair, it's like a pair, that's what an octuple deformation means, then there is an incredible field between the silver and the francium. So the you see silver when it these are calculations when it reacts with francium, it produces a molecule which is very polarizable, it's very good, and it will have an effective field which is much larger than anything that any other molecule can have. So since there should be an electron here, and then there may be, but there are many other things, then that is the guy that you want to do the experiments with to look for parity validation. Now, before I continue, I should say in this very important year of the quantum, as the Rolls reminded us, it was 100 years ago that Heisenberg discovered quantum mechanics. But if you have read the original paper, he said that he was interested in formulating quantum mechanics based only on quantities that can be measured. And what are those quantities? He said to us, the energy levels or the frequency of the light emitted and the intensity of the light emitted. Now I show you the one that measures the rate. So the light emitted, how does the light emitted changes when you change the system of coordinates? That's one of the things that we can do. That's a quantum measurement. And the other thing is this one. This one is you will get a shift. If you put the electric field in one direction, the energy levels will shift and the frequency will change. So this will measure a frequency change. And as you know, and we were told by Steve today, Steve Chu, frequency is the best thing we humans measure. And I think Johan Katermi said this more than once, change your problem to a frequency and you're home. Modify it to a frequency, okay? If not, well, measure a rate, okay? So that's the plan here. And we put together, fortunately, Dave is the head, he's still in Chicago and will be moving, I think officially in January of 26 to Hopkins, although things are happening already in Hopkins, right? There's people from Triumph. I am still hanging around on that. People from SFU, people from Manitoba, people from UBC. So this is a fair number. And the idea is to improve the sensitivity to a CP violating proton shift moment using the 223 Francium series. So you may actually ask a very honest question, and how do you make a francium silver molecule? You don't call the chemistry company and say, okay, could you deliver some francium silver? Even Marguerite Perret would not be able to do that, and she did discover francium. So the idea is a beautiful idea. Imagine that you have two atoms, an atom which is francium, an atom which is silver. And let's imagine that they are going to be colliding slowly. So these are very cold atoms. They are in their ground state. And this is the internuclear separation. But the key part is that they are not going to collide alone. They're going to collide with a laser that goes to the excited state. So you see, if you hit them at the right place, they can go somewhere here. And now you see this is a bound state of the molecule. And then that molecule can decay. But we want to actually do experiment. This is called photoassociation. Okay, so it's just you don't collide the two atoms alone. You need a third body, and that's the photon. Okay, and then it does work. Life is a little bit more interesting. Oops. Life is a little bit more interesting, and there are lots of other energy levels and so on and so forth. But you have to look at the Clark-Gordon coefficients and that, but it's all possible. So with that, you can see I told you some history, some story, and something to look forward. I hope in the next 2 or 3 years you will hear about the parity experiment. And if I'm very optimistic, in the next 10 years, you will hear about the time reversal result. Am I optimistic about the time reversal result? Look, I'm going to say a very personal but very striking answer. The first time I was talking one-to-one with Norman Ramsey, I asked Norman, "How are you, Norman?" "Still measuring zero." And I think by that time he was this Nobel Prize, this incredible guy. I am still measuring zero. Okay, so all right, but with many digits. And with that, thank you very much.
Question from audience?
Oh my, thank you.
So I have several questions.
Oh wow.
Is there an intuitive way to understand the E scaling to the cubic or to the 8/3 power?
Okay, let me try to remember the argument. What you want to know, the Z scaling,
The Z scaling?
there is the most important part is that the S state, how does the S state in a hydrogen atom scale with the wave function? And it actually scales as C to the 1/2. Then the P is actually C to the 3/2. And the other C comes from the interaction.
Yeah, but so the Z cubed is just a phenomenological fit to the high orders atomic numbers, or is it something from?
No,
from
it does. I
atomic
just
model?
said it based on the hydrogen atom, which is something I can still, I think I can do, but if you go, it remains. And let me just, the C to the 3/8 is a little bit more complicated. 8/3. It is it has to do with something that is called the anapole moment. Okay, and so just let me leave it like that. But so you still have the, so you will end up instead with
You showed a plot of the Wilson coefficient structure of up versus down for the APV for cesium. Do you have a projection for what you expect for the francium?
actually I took it out, but the answer is something which is I may be able to. No, because I don't think I took it out. I think I I hide it. So let me see if it's still there. Then I no, I am afraid I did take it out. So the for the this I remember by heart. For the if we are able to do it with an odd isotope and with an even isotope, we may even actually get a crossing. More or less, but that's incredible. Okay, but but I said you need to change the.
On the final proton ADM, you said 10 to the 4 improvement with respect to current thorium oxide?
No,
Or
come on,
with
thorium
respect to- or
oxide
what's
is
the-
passé, right? It's Eric Cornell's number, right? With ions. With what?
I don't remember which system it is.
Nor do I. Let's see. I don't remember, but it's about a factor of 3 better than thorium. It's not factor. No. But you see, factors of 3 in our game are usually the lifetime of 2 graduate students. Okay. Thank you so much for your interest.
Thanks very much. Any other question? Okay, if there is no question, the speaker
Thank you
again.
so much.
Yes. Okay, happy ending of today's talk.